And welcome to the third in our series, an introduction to artificial intelligence. This is the third tutorial, and it is the advanced level tutorial. We already had we've already had a beginner's tutorial and an intermediate one. Next week, we're going to specialize on XKool LookX. The following week on text to video, which is a very new area to be researching. Then we have a roundtable discussion, a panel discussion, the AI design revolution, including a number of significant figures, including Patrick Schumacher. And we end the series with emerging female voices in AI. We've come across a number of super talented female voices. Today's session, we have someone coming back, George Guida, coming back by popular demand. George, he teaches at the Harvard GSD. He's also involved with Daniel Escobar in a startup, Xfigura, which is a generative AI startup. We also have Karla Saldana Ochoa, who is an architect originally from Ecuador. She completed a PhD at ETH Zurich, and she's now an assistant professor at the University of Florida. We have Julian Besems, who is Dutch and who studied architecture at Newcastle and UCL London, where he was also teaching. He's also studied computer science, and he's currently undertaking a PhD in ETH Zurich. And we finish off with Serjoscha Duering, who is from Germany. Serjoscha did his PhD at the Austrian Institute of Technology. He's currently teaching at IAC, and he is also working for a company, Rehab Forge, in Berlin, in Köln. This is the image for Serjoscha, multimodal LLMs in action. Karla Saldana's image on AI design with big data. Julian's image, perceiving domains of information. Finally, to just mention that tomorrow I'll be giving a talk as part of the parallel series on artificial general intelligence that is going on Sundays. We've already had two very significant speakers. Ochoa, the first session, who was attracting a lot of views on YouTube. Stuart Russell last week. Myself, somewhat of an imposter here in the presence of such luminaries. Next week we go into the world of design. And then we have Blaise Guiriakos and Carl Friston finishing off a really remarkable group of individuals. I will stop sharing now and hand over to George. George, welcome.
Thanks so much, Neil. It's great to be back for, I think this is the third time. Yeah.
Yeah, by popular demand. Thanks.
All right. So I'm going to dive in today. It's going to be a brief workshop into 3D AI and how this applies to architecture. It will be mainly how we can convert text or images into 3D. There's a lot of new startups and new companies that are emerging in this space, but we're going to focus mainly on this 3D generative side. So let's see if it works. I'm going to start by giving a little introduction, a little framework on where we are with 3D today, starting from image and leading to 3D, open source and closed source tools. And so that's going to cover, I'm going to try to give you guys some tools out there. So I'll be covering three proprietary, three closed source tools, and three open source tools as well. So before diving deep into 3D, I just wanted to frame and give perspective of how fast we are moving. And this is using the very common platform Midjourney, using that same prompt at the top, a photograph of a multi-story building with timber cladding from the day it launched in February 22 across every iteration to December 23 when this V6 alpha model actually came out. So this progress has really been exponential. we are gradually now able to, we're gradually now able to generate thousands of images in very fast times. We're able to use models that are fully customizable. They're very flexible in representation. People often think they're only good for generating these high-res images, but they're actually also great for those abstract, more conceptual approaches to design. So why is it really relevant to us today, and why has it started getting all this hype and all of its attention? And that's really due to the amount of control we're now able to have in this process. We're able to use these models, apply, for example, control nets, LoRa's. There's a lot of under the hood open source tools which we can do to fully customize those outputs. In this case, I'm hacking, for example, a Gary sketch or hybridizing it with different architects, the Zaha Hadid, the Antonio Gaudí, keeping those coherence over edges. And this extends also into the digital. So you've seen a few examples of these. This image-to-image translation is now at a quite high level. We've seen stable diffusion models. Almost very recently, there was a new model called Flux, which is starting to actually compete with these closed source tools or mid-journey tools, and that's slowly making its way into all of these open source workflows. This is just a preview of some images from a workshop in Minnesota that I taught with Tim Fu. So for images, we've reached this high quality of images. We have very accessible interfaces, greater control, model personalization. Copyright is a separate conversation. It is a hot mess, and we'll see what the courts decide for that. For 3D, this is very much an emerging space. I believe that we're in the same moment in 3D as we were with images 2 years ago. In particular, I say this because of the recent development in the video space. There's a lot of things going on, the Sora model, Runway, Pika, there's all of these new companies that are racing to get that very high coherent video output. Now, what comes with that coherence is that you can then use those images. This is one of many approaches to then create coherent 3D objects or scenes. And so this is a typical 3D pipeline, which essentially from the left, it takes that input. It can be a text input, image input, one single image, or actually composing multiple different images. And then through a series of camera locations, typically we convert that through a machine learning representation, a machine learning friendly representation, which is not typically yet a mesh or a surface. And then we convert that it's very common these days to use Gaussian splats. NeRFs was this precursor. There's a lot of tools emerging in that space. We then convert that into meshes. A very common algorithm used to in that conversion problem was using marching cubes. That's since evolved. It's very challenging point to convert thousands of points or thousands of vertices into a very coherent and clean rabbit in this case. And then the final translation is making it accessible into a user interface. Now, this challenge in 3D has really come due to issues in representation, also computational power. In the AEC industry, keeping control over data or making it accessible to all is also very difficult. We have meshes, we have surfaces, we have BIM models. There's so many different forms of representation that when it comes to training coherent and uniform data set, it's actually quite challenging. Also, you think of the computational power involved, for example, when using voxels. If you want to generate a 64 cube voxel data set, that is a lot of points over thousands of data of 3D models that you have to train. So if you want to increase that resolution, imagine the computational power needed then. So a lot of the development, and I'll focus mostly on this approach, is a multi-view approach. Imagine it's a form of photogrammetry where you can start with a single image or start with multiple images and use those to create through inference to create predictions on what it doesn't see, and then compose that 3D final object. There are a lot of data sets out there that are used to train these models. On the left-hand side, you can see one of the most recent one, which is Object versus Excel. It really increased the number of models available from previous data sets. There was Thingy 10K, which was literally 10,000 3D printing models, and this is now 10 million. So there's a huge increase over time in that data availability. When you think of the training process, it's very much the most time-consuming element of any machine learning or AI training. So then there's a Fusion 360 data set, which really, it takes all of that embedded logic, that drawing the polyline, extruding. So that really demonstrates an interesting new potential. In the 3D or in the architecture world, there's also other data sets. For example, Matterport has one. There's several for interior spaces, urban scenes, or oftentimes people result in making their own data sets. And this is just one example of many. And this is a project I did with Professor Andrew Witt at the Laboratory of Design and Technology at Harvard, where we had this issue of data sets, of data scarcity. And so we decided, in this case, we downloaded thousands of busts, and we used a model called ShapeGAN to train. We're navigating that latent space, this multidimensional solution space, to generate unseen, uncreated busts. And in this case, we tackled it by simply using Grasshopper to create our own synthetic data sets. So we're creating these abstract mathematical forms and then seeing how we can interpolate between one another. That has since developed into different forms of different types of model. This is one example, Point E, which then developed into Shapey or Shapey, which essentially streamlined this process and used a series of 3D models and converted those into rendered images to then train a process based on those rendered images and a point representation of about 4,000 or so points, which made generating any of these 3D text to 3D or image to 3D models quite fast. For those who are interested, last year's workshop was introducing this idea of neural radiance fields and how we could essentially take, for example, how we could take a Rhino viewport with a Grasshopper script and essentially export all those camera data points and then run an image-to-image process on each of those frames with that specified camera transform file, and then plug those two together and put those into a neural radiance fields and combine those into a 3D scene. So in this case, we're going from Rhino to image to text, Rhino to image, so we condition that output, and we start getting these 3D editable meshes. That's since evolved, and with Daniel Escobar and Carlos Navarro, we continued that project into just reimagining how this could be plugged in, for example, with the Google Maps API. Could we scan sites and then start reimagining our cities, either simply with text prompts or in time with also image prompts as well. And so these are just some examples of really showing what happens under the hood with all these models, the pre-processing, the canny models, the segmentation. We use a lot of these to really try to make sure that final 3D output was as high res as possible. So we're scanning that site, we have those camera locations, and then we're recomposing this into a 3D edited form. And so we went from the original, this is the Prod Museum, it's more of a speculative project. We're looking into applying this to embodied carbon issues, how we can reimagine our cities and democratize that process. And so here this project extends to agent-based simulation, and starts using agents in Unity, it gets a little more conceptual. But it's really promising to see how we can start using these tools in other use cases. So again, video is really going to change this landscape of 3D, which brings me to the next part, which is a bit of a tooling. I want to make this as useful to you guys as possible. So I've wanted to give you three closed source tools and three open source tools, and by giving you a Google Colab of one of these. And so one of the first ones that I use often with my students, it's the hello world for me, is a tool called CSM. CSM is a really simple to use. It's image to 3D. All you have to do is upload your object. You click, with one click, you can segment that image, remove the background so you're not distracting it from in that inference process. And then you're creating, in this case, a chair, which it's, as you can see, it's always going from that single image to then create a fully coherent 3D scene. Now, it's important to note it's not a perfect process, so it's always iterative, and we're in this interesting moment where we can really keep our agency in the design process and start manipulating editing and having control over what that mesh output looks like. I've been working with Monday.com, it was also in collaboration with the Department of Education, to really bring these tools, to bring AI and 3D printing, to really empower underprivileged students in New York, their high school students in this case, to use these tools to give them access to the tech industry or tools of tomorrow. So you can really see this push towards 3D or democratizing these tools is really having pretty impactful impacts. And so students were asked to reimagine the future of New York. We're going through a second program now across about 15 schools this year, is rising exponentially. However, we're training them, we're teaching them how to keep that criticality within the design process, but really leverage these tools to augment their imagination. And so this really relates to something I teach at Harvard, and I also have been teaching the kids to start using these tools as a process of design thinking. These are tools which enable you to solve multiple problems. On the left side, you see the problem space. On the right side, you see the solution space. It's really great to see how these tools are developing. Rodin is another really interesting one. Its results are very accurate, so I do invite you to give that a try. This is an example of a chair that I generated from, again, that single image. And so that intricacy, that segmentation that I was able to do over that single image and generate this very coherent output is quite impressive. Now, this would need post-processing, a lot more work to get it into production or to finally 3D print it. Mesh is also an interesting one. Again, that image to 3D. This was done a few months ago, so I'm sure it's much better now. Okay, so this brings us to the open source category. I'm always an advocate. I teach this in all the classes that I've taught at Wentworth, at Harvard, and across several conferences. So we'll be covering three models in particular. The first one is called Large Multi-View Gaussian Model for high resolution 3D content creation. It was a paper that was made available in February. And so this is a Hugging Face link. I think by now some of you are familiar with that website. Hugging Face is one of the best open source platforms where you can access the models, the data sets, and actually this is one of the spaces categories where people publish a simple, accessible user interface, and you can simply drag and drop or add in a text prompt and generate these different results. So this model was trained on about 80,000 models. It was a subset of that object first data set, and you can generate results in about 5 or so seconds based on that Gaussian splatting approach, that Gaussian reconstruction of this multi-view process. And so it does different elements. So it textures that image, it does the UV mapping, And you can also export this in multiple formats. Its use cases are pretty broad. It's currently most used, for example, to create gaming assets or in the augmented reality, virtual reality space. It is slowly making its way into architecture as that resolution gets more and more gets improved, and as we have more and more control over that process. Another model which has recently come out is called 1, 2, 3, 4, 5 plus plus. This is every few months a new model within this lineage comes out, but this essentially is again a single image to 3D multi-view generation process. And so you're able to input that single image, and then it generates multiple images of that single image, and then textures it and creates a fully coherent object at a pretty impressive resolution. So this brings us to the one that I wanted to preview to you guys. This is one made available by Stability AI. Obviously, they've they've made available lots of these their models. And what's interesting about this is there was an emphasis on the generation time. So it only takes about, they claim at least, 0.5 seconds to generate a final output. And it's built on a previous model that they've open sourced as well, called Tripo SR. I know the next version, I think, has just came out about a day or two ago. But this is a really interesting hello world, let's say, into this tool. So I invite you to open this link. You're welcome to try it another time. And so what I've made available is a Google Colab, which essentially will permit us to simply walk through the process, understand a little bit of what's under the hood, and hopefully this gives you an understanding of how you can use the same approach but be versatile to use any of the other open source tools. So for those who don't have experience with Google Colab, this is a web-based Jupyter notebook. Imagine it as a Google Doc, which you can use in different codes, different coding languages in it, and you can share it with your friends and whatnot. I've added some resources right at the top. So here's the GitHub repository, which gives you all the information, all that open source code, just to show you what's behind and give you more information about what dependencies you need. Every GitHub repository gives you that basic amount of information. And so I've tried to make it as simple as possible. So the way it works, if you do have a pro account, I always do advise to use an A100 GPU. And if you're want to make this your own, write notes in it, I always advise you, when you get a Google Colab by someone else, do save a copy in your drive, because any edit you make on this then get, let's say, forgotten. So Google Colab has been a really great resource for any of this like ideation, this testing before that production or before putting things on web. And so the very first cell right here, these are called cells, is to essentially clone this GitHub repository. So in this case, it's using Instant Mesh, and we are accessing, oh, this is actually for Instant Mesh, yes. And so one way in which you can prepare to use this is you can just upload a single image that you have on your computer, or if you're curious to try this new model, parametric house beach. Again, this is in the Spaces tab. We're using Flux, which is Black Forest Labs' latest model. And this is just a very simple way of generating image quickly. They've made pretty powerful GPUs available. There's some other models you can also access. And so just in a few seconds, this is completely free. You can actually generate some of these famous, you might be seeing on Instagram, some of these images with a really high quality. And there's some advanced settings there. So what you can do once it's generated, you can see this diffusion process. it's generating that output. And I'm going to download that image and just show you how to image one. So I've downloaded that image. And what we're going to do is use that image in just a second and then upload it to then try to create a 3D object from that. So we're first running the first setup. So all you have to do actually here is run that play button, and that runs the cell. And then what we're doing here is we're uploading our image into it. Now to upload an image, all you have to do is, for example, I have images here. Right? If I have that image, let me see if I can pull it up. I can just drag it here and it'll say, you can skip that warning. It is in the wrong format, so it would have to be a screenshot in this case, or download it as a JPEG or as a PNG. But the idea is that once you do upload an image, and this is one from the cover, from the preview of the workshop, that's one of the images. It was generated also with Flux. And you can simply right-click, copy path, and then replace this path here. Once you run that cell, we're essentially downloading the Hugging Face diffusion pipelines. We're using 0123 plus, and we're running Instant Mesh. And essentially what it's going to do here is that it's going to download the weights of these models and generate that multi-view process. Going to generate these different images from different perspectives of that building in this case. And so then comes the actual reconstruction. And so once we run the reconstruction cell, we're able to get a somewhat of a coherent 3D view of what that object looks like. And so it's not quite perfect. I could have picked maybe a more symmetrical view, a more cleaner view. I did give it quite a hard task by having something with quite a sharp perspective, but I do invite you to see if it works on other geometries. And so the final step is to preview that geometry in 3D. I added, this is with Plotly, one of the libraries. You can simply preview that geometry. I might add the texturing onto this just to make it easier for you to preview it. And then at the end, you can export the zip file and manipulate that geometry. This is going to be an OBJ file. And so you can bring that into Rhino or whatever software you're comfortable with. I am going to open it just so that you have a preview of what that looks like. And open this. Because these are meshes, sometimes they're not as Rhino friendly. So I do encourage students to use tools, for example, Mesh Mixer. It's been discontinued, but they still make everything accessible online. It's a very simple to use tool to smoothen geometry. It's kind of that sculpting approach that you might have from Blender, but it's even easier. So there are things like flatten. There's a lot of brushes out there. So you can see, I push too hard. You would change the settings here, or you can simply click on drag if I want to get that cantilever to be a bit more pronounced. You can pull that out, and you can have quite a bit of control using this tool. But the point I'm trying to express is that you can take this geometry, use it within your current workflows, or use it as an inspiration to then remodel or make new shapes or make new massings. So we are still in those early phases. There are other tools out there that give you more of that like massing optimization or structural optimization tasks. However, this is more in the ideation stage. So you might remodel this, or you might work with that mesh and actually clean it up. Okay, so hopefully that was a very quick but nice little introduction into Instant Mesh in this case, and give you a glimpse into the open world, this world of using Python or using Google Colab notebooks. There's a lot out there, and so I'll very briefly preview something Daniel Escobar and I have been building in the last few months. This is just a small snippet of the various functionalities that have been integrated into. So we're using, for example, stable fast 3D. We're using other models, so it's essentially a collaborative platform for architects and designers to really have be able to ideate in a collaborative way on web and with other of their peers or other students, for example. And so we'll be making this available at the coming weeks to select few people and then launching it hopefully very soon. So for those who are interested in diving deeper into the Gaussian world or the neural radiance fields, feel free to look at last year's workshop, or feel free to also email me if you have any questions. So I do, as part of my practice, Architag, we offer AI design consultancy for architecture firms, and have made this preliminary map, which is part of a larger, about 150-page report, which we're about to publish very soon. About the top 50, let's say, it's a preliminary list, AI and AEC companies that are out there. And what you can really start seeing, the reason I'm bringing this up, is that the amount of interest in this 3D space is actually exponentially increasing. And so clearly there's this big question of what is the future of BIM? What is AI BIM? What does that mean? And so lots of these companies are really pushing towards massing tools for optimization. So you have, for example, TestFit or Spatial. There's in the floor plan generation, Finch is really standing out. There's urban planning or real estate tools, for example, CEDAR. These are just few of the very many that are coming out. And so what I gave you a glimpse is more of that ideation phase, but it's always important to understand across all design stages, there's a lot of development. So it's been a pleasure and hope you've enjoyed this. Feel free to reach out to me if you have any other questions. Thank you.
Thanks, George. You make it sound so easy, but but that was terrific. You covered a huge amount of ground there. Can I just ask you just one question? It wasn't totally clear to me. What is Xfigura doing? What gap is it filling in the marketplace? What is it doing that others don't do?
Yeah, so we are catering it to be specifically for architects. It's imagine it more as like a collaborative Miro for architects. So what I've not shown is that we fine-tuned several models, they're LoRa models, but also 3D models to make this process. You can see that 3D generation, it's not quite perfect. And there's not a lot of resources putting into architecture data sets specifically. So we're trying to make it industry specific. However, it is offering tools that many other platforms actually do offer.
Okay, great. Just one final question. Have you heard any rumors when Sora is going to be released? Some are mentioned September, but running out of days now.
Yeah, it's always been the end of summer push, and I'm still waiting as well.
Yeah, great. Thank you, George. That was terrific. Thank you so much. So we're going to move on to Julian now. So the order, just to repeat, is going to be Julian, followed by Karla, followed by Serjoscha. Julian, would you like to share your screen?
Yes. Let's do that. Okay. All good? Yes. Okay, so thanks for inviting me for this. The things I'll be showing is maybe a bit less focused on actually producing anything, but more of a introduction to how to think about these outputs from machine learning and their context in a vectorial space. So, and the primary means of looking at that will be using a pretty old model within the types of neural networks, which is a self-organizing map. So a self-organizing map is a means of creating a topology that represents an overall domain of information. And that information is then embedded in any form of vectorial feature vector. So I recommend actually having a look at the Wikipedia page, which is quite useful. There's images from that as well, which shows a two-dimensional training process of a self-organizing map fitting to 3 clusters of data. And also a more extended article is by the creator of the self-organizing map, Tove Korhonen, in this publication, which speaks a bit more about why a self-organizing map is interesting. So I'll immediately jump into how to think about this type of model and what you can kind of use it for in terms of understanding domains of data that you might be working with. So the first one is, how does a SOM map out that domain of vectorial data? And what we'll start with is just color data. Oh yes, the self-organizing map library that we'll be using is developed by Nikola Marincic. So it's this GitHub, which is very quick and simple to use library to get started with self-organizing maps. So I definitely recommend that library, and we'll be using it throughout this tutorial. I'll be running pieces of the code and where it's quick to run it, and in other parts I will kind of just show the outcome. So if in this case we take 200 colors, so here this means random NumPy random, we take 200 colors, which is 3 dimensions, and we shape that into an image to just see what our training data is. So we'll start with RGB values. So red, green, and blue, those are our 3 dimensions. So if we take the first data point, we get vectors that look like that. So for those of you not familiar with what a vector is, it's essentially a list of numbers. And it has a dimension. So a vector in this case has 3 dimensions, but it can have, within a mathematical construct, it can have any set of dimensions. And the important part is that vectors, and why vectors are the dominant way of encoding data to work with them in a machine learning context, is that it allows to measure difference. So if you have an image on its own, but you don't specify the means of how to differentiate between one image to the other, you can't train anything on it, because the training process relies on being able to measure the difference from one thing to the other. So in this case, the distance measured between colors, we'll just take the linear distance. So as if you would plot it on a 3D map and just draw a line between them, which is called Euclidean distance. There's many different distance measures, but that's the one we'll stick with for this tutorial. So we have 200 colors, and we start training a SOM on it, where we take a SOM size of 50 by 100. So we have a map of 50 squares by 100 squares. And if we show the self-organizing map without any form of training iteration, so only one training, we see that it's basically is just noise. Then if we start training it for 100 iterations, you start seeing that the self-organizing map starts to fit to an overall differentiation between where these different colors might sit in terms of how close they are. Doing that for 1000 iterations, we get a nice spectrum of colors that grade from one place to another. Doing that and looking at the internal distances. So this means that you take one square in the SOM and check how far that particular square is to the ones next to it. Because what's important to understand is that here, this doesn't actually show the training data. In the same way that this image, you see that the nodes of the self-organizing map, they kind of float in between the actual data. So that means that with less information than the overall representation of the overall map, you can still get a smooth topology of how that net, or the self-organizing map in that case, starts to represent that overall topology of information that it tries to represent. Which then here it shows the internal topology, where you see that it's not a nice square representation, but there's unequal kind of distances between areas. So here you can see where the green actually moves to the dark blue. You see that there's a larger internal distance between the squares of the map. Same here, of the orange to kind of the purple. There's like peaks and troughs within that topology. Doing it for 15,000 iterations of training, you see that it gets more compartmentalized and more patchy, which also is seen in the U matrix of the SOM. So you can see that it starts to really condense, and the parts that are of the nodes of the SOM get pooled to certain clusters of colors, which is then more close to the reason why if we only have 200 data points, it starts to become patchy and go towards that. So that's a very kind of simple visualization of overfitting of the map onto the data, which can be seen here. Okay, so that's with colors, which is, I always think it's a useful means to kind of start with, because then we can still kind of imagine how you can measure the difference between one color and another. However, if we then start with black and white images, so we take the fashionist dataset, which is kind of a standard dataset of fashion images. And we take the 10th image, which is this black and white image of a dress. That image is in itself, in the data points, it's represented by a 2D list of what's the width? 28 by 28 values, where the values are the brightness of the color, which then we have a problem because we've got a two-dimensional data point. So this data point has 28 by 28 dimensions, which we can't fit into one singular line of data, which would be the vector. So what we do instead is we just flatten that training data, and then we get 60,000 vectors of 784 dimensions, where one dimension of that looks like this. So if we look at that same dress here, but we simply put all of these lines onto one really long line, then we get a feature vector that looks like this. I mean, I made it a bit thicker so that we can actually see it as an image, but it's one line of pixels of 784, and the values stay the same, but they're just flattened out, which isn't a very clever way of vectorizing it, but we'll see in a moment that it does actually work. So taking 10,000 images of that and putting that on a self-organized map of 25 by 25, we get we can train it, which I won't do because it then takes too long, but I have pre-trained it earlier, which then gives us an image like this. So I'll open that quickly in a new tab. So here, we're now looking at the actual SOM in the same way that earlier in the colors, recall that this doesn't actually show any of the data points, but it shows a topology of a mapping between the original training data. This SOM has seen 10,000 images of clothes, and it starts to create a topology that looks like this. So you get weird moments where kind of dresses and shoes starts to merge, but you can see that it represents the overall pieces of clothing in a very smooth fashion. So trousers go to dresses, go to t-shirts, go to pullovers, and then via a long way around, they go to bags and shoes. But none of these are actual real shoes or real trousers. They are in between things that seem to be similar to the other points. So then to actually see of what those points are closest to relate them back to the original data, what we can do is that we take for each point in the self-organizing map, we look in the entire data set what the closest original image is. So having a look at that, instead, we see here that these are all the original training points. So every cell looks for the training value that is closest to its actual thing. So here, what you might also notice is that many of them go for the same one, which means that this shoe is the closest point in the data to these 3 points in the map. Then finally, one other way of looking at the overall topology is to instead do it the other way around. So instead of looking for the closest data point to each part of the SOM, we take each data point and project it onto the self-organizing map, which ends up in three parts of the self-organizing map which are empty because none of the clothes are closest to that one. But we get an overview of how you can see this overall domain of clothes mapped and how they transform from one to another. And just to go back to what those cells were in the original one, where it's just showing that, it kind of makes sense because it's these weird in-between moments between a dress and a shoe where it doesn't really represent anything anymore, but it's a necessary transition, which means that there's a certain distance in a data gap between these points. Okay, so that's for the kind of initial data points. Then one more thing that we can do with that is that we can activate the overall sum with one data point. So if we take the first piece in the data set, which is this particular shoe, and look at all of the cells in the self-organizing map and take the distance to this particular shoe, we get this outcome. So that means that this shoe relates to this area in the overall map, and it doesn't really have any other interest. Well, a little bit over here, so it's still a bit more interested in what's going on there, but it's mostly very strongly in this area. Okay, that's for the overall general introduction. Now let's look at something a bit more exciting. So if we take all ArcDaily projects on ArcDaily from the last 3 years, and we first start looking at its images. So one example of an image, if we take this project, a recent project by Ishigami, which is a museum, then we need to find a way of actually encoding these things, because an image, yes, we could do the same as with this, but then we would have to take each RGB value, triple it, and lay that on a really long line, which probably is also not a very good representation because this data set is very standardized. So that's why we can get away with just flattening it. But with these images, we need to find another way. So what we take here is the efficient net model, which is a classification model of images. And we chop off the last 3 layers, which relate to what the actual categories are, and look at its embedding before that. So what this deep net used to classify images and what it focuses on, we take that set of vectors or set of neurons, treat them as vectors, and that's what we're going to use to train the self-organizing map on these images. So we take this image, take the feature vector, then we get an array of values which has a shape of 1,280 dimensions. So we get a really long list of values which represents kind of what's going on in this image according to the large pre-trained data set of that model. I then did this for all of the projects. So I've got a project dictionary of all of the projects where each project has a set of attributes in the dictionary. And if we look at just the URL, so let's have a look at this particular project, which we'll be using as an example. So what happened for the dataset is I took all the images that are on here and all the text descriptions and saved all of that so that we can then start looking at this overall domain of information of the last 3 years of ArcDaily, which ends up in 5,251 projects. So it's not a huge data set, but it's sufficient to be able to say something about them. So the first step is to take all the images from all of the projects. Don't worry about the code too much for now. So I'll share a Google Colab version of this notebook and annotate it a bit more so that you can either use it with your own data set or get into the code a bit more, depending on your preference. But what happens here is I take all of the feature vectors that I encoded of all the images and put them on one large pile, which ends up in 158,000 images, where each image has that dimension. Which then, if we train a self-organizing map on that and then do the projected representation, this is the self-organizing map that we get. So this is 30 by 30. So we get an overview of, if my laptop is happy to carry on with this, I'll just close those other tabs because they're quite big. So this is an overview of all 160,000 images on ArcDaily from the last 3 years. So we see very clearly that it starts to kind of put technical drawings in one corner, kind of outdoor renders or photos in one area, and the indoors go into different places. But there's enough kind of distinction between types of indoors, what kind of perspectives they are, and also the types of buildings start to kind of show up in this overall mapping of the total domain of images. But then it gets a bit more interesting if we start to interact with this. So if we take one image, so we take our original image back and take the image feature vector and we activate that, then we see that that image likes other images in this particular area, which if I plot that one, so activator here, this is the highlights of where that image likes to sit and what it's interested in. So these cells are kind of what resonates. So it's outdoors, it's got things with water and overall large views of mountains, which is what that particular image kind of looks at as well. So you get an idea of other projects that speak about similar things. So then, because the nice thing about this data set is that we have projects with 20 to 60 different images. So if we take all of those and map them onto, take all the averages and take an entire project and look at what that project is interested in as a whole, we get this broadening of the scope of what it looks at. So we then see kind of some parts of the internals that are similar and other projects as well. So if we then, for instance, take the cell 2323, we can have a look at which other projects are in that cell that is really strongly kind of lighting up when we want to look at that particular Ishigami project. And we see these 6 images are in there, which is these 6 projects. So if we want to have a look at another one, take a look. So this project seemingly is kind of similar to that museum of Ishigami that sits on the lake. Now, I think we can kind of see why that shows up on just purely an image-based representation. So looking at a couple more, so this is the just a smaller representation of it. So this is the overall map of the museum. Another Ishigami project sits in some parts, it sits quite close, but it's a restaurant, so it has other emphasis. And 2 OMA projects, of which one is a store. So we can see that it really shifts kind of its focus in what other images it actually relates to, as you would expect. So this is the OMA one. Another OMA, more commercial office project over here. Okay, so one small test, which is, I mean, I have to admit, I am not very good at creating images with generative AI, but if we take a very simple DALL-E outcome of an image and look at which existing projects in ArcDaily are actually kind of similar. So what does it resonate with? And I think this is where this, in the context of generative AI, becomes really interesting, because you can, I mean, I now took quite a generic data set of ArcDaily, but if you have a very specific interest in the project that you're developing and you have a kind of a data set that is curated to that, you can start working with these very generic generative AIs and kind of reflect on which parts of your data set it's actually relevant to. So this particular one, this likes these areas. So these projects or these photos from projects are what this fairly generic, boring generated DALL-E image speaks to. It's kind of interested in projects that sit around here. So kind of the thin structures, and you get more examples of what kind of imagery that speaks to in existing things, which then also allows you to look at what are the internals of these projects, what are the other kind of contexts, and how do their architects speak about that. So then if we leave images there and instead look at the text descriptions of each project, I'll go a bit quick because I think I'm getting to the end. So I took all of the descriptions of the projects. Then you need to do a bit of pre-processing. So you only take the core kind of words. So this is the entire description of the project, but that after pre-processing looks like this. So you only take the words that kind of have meaning and you stem them, you lemmatize them. And after that, we train a model on all of the text data, which is vectorized by using a TF-IDF. Look it up if you want. And then after that, a dimensionality reduction using truncated SVD, which gives us vectors of each paragraph in 100 values. So a 100-dimensional vector represents each overall paragraph, which then if we start putting the keywords of each of the points in the self-organizing map and render that, we get this map. And remember, this map, it looks the same, but it has nothing to do with the images. It's changed completely, but we now start to see, okay, so if a project speaks about water, it also often speaks about a lake, a space, a site, and a roof, but also next to that, it starts to go more towards experience. From experience, it goes to city, site. So you can kind of see how do the projects on ArcDaily speak about different concepts and how do they flow from one to the other. So then if we activate that with a project description, so if we go back to the storefront, the Tiffany temporary store by OMA, which in terms of its images, it was looking like that. Now, based on just the descriptions and the description of the SOM, so for text, we're using red, for images blue, so that stays consistent. It kind of speaks about these terms here, which sit around here. So store, brand, space, customer, design, experience. These things are important in that description. To the restaurant by Ishigami, that's what it looks like. And the original art museum that we were kind of working with as our example project sits in this area. So blowing that up further, we kind of go to the area. Sorry, I need to get rid of this blue stuff. Let me just open it. Yeah. So the area that project speaks about is mostly with the keywords of water, lake, building, site, space, water, tower, building, and in that it sits mostly very strongly in this specific cell of 318. So having a further look at 318, then we get these projects sit in there. So there's different projects that all mostly sit in that specific cell and are kind of the friends of that particular Ishigami project in terms of its description. So looking at that further in what that activates in terms of the images. So now we're looking back at each project that sits in this cell and project those back onto the image SOM, we get these differences. So you can see that there's kind of similar parts. So projects that speak about lake and views and experience, obviously the images are starting to get quite similar, but there are also outliers. For instance, this, I think this project, so number 4, has a very different emphasis in terms of its drawings than in terms of its language compared to the other ones. So I have a quick look, which kind of shows up. So even though it speaks about those concepts of water and lake, the images are very different from what you would expect. So it kind of shows also a bit of the differentiation in terms of how language and image do stand separate from each other. And there's a difficulty in kind of collapsing those two domains entirely, which is why it's worth also in terms of a bias and creating your own data sets, you can start kind of reflecting on where are the outliers, what kind of projects speak about it in a different way in relation to any generative work that you might be doing. So taking the average of that entire cell and projecting it back to the images, these are the images that that cell particularly looks like, which if you recall, it's actually, it does still have a heat kind of, it glows up most around this area, which was also similar to where the project of the Ishigami project was lighting up in the original one when we were just looking at images, but it broadens up the scope of investigation a bit more. Now, as a last step, I take the prompt that I created that DALI image for and look at where that is sitting. So I kind of wanted to have a similar place to the Ishigami project. So I was saying, okay, a museum built metal structure sitting on a lake, see where we end up. So we end up just one cell further onwards. And if we do the same exercise, so look at the project that sit in that cell based on the description and map that back onto our domain of imagery, we get quite a different emphasis. So that project, based on its description and, well, based on the prompts that I give it, ends up at mostly looking at this area, where it has a different kind of resonance, and we look at mostly the thin weight structures really shows up. And yeah, that's kind of my take on how you might start using self-organizing maps to kind of start seeing correlations and work with an overall domain of information and kind of get a grasp of how you might think about a vectorial embedding a bit more than just a singular generated output, and kind of start contextualizing that into a data set with specific biases of your own. So I think we'll leave it there. I'll upload a Google Colab version of this where it's a bit more curated so that you can use it for a set of images and a set of descriptions that you got from somewhere to start playing with that a bit more. But I'll update that by end of today, and it'll be this link. Okay, thank you very much.
Thank you, Julian. That was we're ratcheting things up, it seems. I mean, this is terrific. I just to say, because you're kind of speaking into the void, as it were, probably not sure who is listening, but I can tell you that one of my own doctoral candidates, he's an adjunct professor in the world of fashion, was taking notes and sending me saying this is amazing. So you've got a fan club out there. That's terrific. We can now move on to Karla. Karla is in Gainesville, the University of Florida. She's from Ecuador, and she studied ETH Zurich. Karla, great to see you. I will be seeing you in person later this week. So, or next week rather. So anyway, welcome.
Yeah, the same. Well, I'll be seeing you in October 2nd. You're coming to University of Florida to give a lecture. First of all, thank you for the kind introduction and for inviting me to give this tutorial. I'm going to share my screen so we can go ahead and I can share what I've been preparing for Digital Futures. So I created a web entry for today's tutorial. So if anybody wants to follow along, we just need to type AISureLab.com. So that's the website of my research laboratory, and the tutorial that we're going to be doing today is on the tab of teaching. So you can scroll down at the very end where we get to tutorials, and is this one, which is called AI and Instrument Capturing a Conscious State. So this tutorial I created based on the previous lectures and tutorials that Digital Futures has been hosting, especially basing some of the assumptions, or at least speculations and hypotheses on Joscha's idea of art as a capturing a conscious state, and then as well following some of the more, let's say, real life or trying to find an optimal state from Stuart Russell. So today, I just also bring a little bit of background. If you want to follow along, we're going to be working not with generative algorithms, but we're going to be working with search engines and classifiers. So here is a bit more developed idea of some of the algorithms that I'm going to be working on. So you can look at this. But then here, at the end of the page, you have two files. The first one is when you click, it's going to lead you to a PDF. And this PDF is quite interesting. If you open it, I have created a list of data sets and a text description of what we're going to be doing today. So if you click on any of these images, you'll see there's a short description of what they are. So this data set is about more than 3,000 images on satellite images of the 5 biggest cities in the world. We have the databases on Street View images. The same goes to them. So if you click any of them, it's going to open up and will give you a sort of data sets. We have a data set of before and after natural disasters. This was related to my PhD, so I thought I will create this file, so I'll share every data set I have collected throughout time, so we can start playing and talking about some of the things that I'm interested in. But today we're going to be working with these 4 data sets, or any of these data sets that are standing here. So after Josh's back lecture, I started thinking about spirits, and I've been talking with my colleagues here at University of Florida, and one of my dear colleagues sent me the reference of Georgiana Hockton, which I am deeply fascinated about. So if you just quickly search online about her, you see that her she's from the 1800s, and she was working on even before contemporary art, this idea of capturing spirits. So I think today's class we're going to be thinking about this idea of capturing this conscious state through a approach of how do we create something without how do we talk about concepts that are not quite realizable, but are interesting to think about space with them. So, all right, with that said, you'll see some of the description of what we're going to be doing today as well. So one of the first things that we're going to do is talking about feature vectors, and that's why I asked to be after Julian, because I'm going to kind of give other examples of how you could encode your data, so these algorithms can see it in a different way or read them in a different way. And then as well, some of the process that we're going to be doing, what I expect but what I play with when I think about creating atmospheric images of perception and concept, and then how we can start thinking about space with them. So let's do this. If you've downloaded already the code, it looks like this. So we have this is a Word for Mathematica notebook. I decided to work in this way because I have to install nothing. I don't need to install set up an environment or install libraries. Eventually, I will be transforming this notebook onto Google Colab so I can share that with you. But today we're going to do it in Mathematica. So today is a version of last night, which is September 20th, and I'm gonna zoom in on my screen so we can see it better. So we're gonna be talking about feature vectors and how do they work, right? So we're gonna simply test out two data. So we have images, which look like this, right? And we have a text. So we are collecting some samples of this text, be or not to be. And we're going to be playing with them and extracting feature vectors depending on how we want to see our data being represented. So the first thing that we saw with the colors in the first example with Julian was to identify this image or an image based on its pixel values. So here we resize the image, and then we are going to encode this image by looking at the RGB values that are on this image, and then flatten them to create a feature vector with several dimensions. Another way that we can look at our data with is by looking at the texture through an algorithm that is called edge detection. And here we're going to count the percentage of black and white that happens in each of these in square images. We can also do it through a much more complex model. This is using BGGNet. And here what we're doing, I'm going to run this, and it may take a little bit of time, but here it's defining an object classification. So it's telling us in this image that we see over here, what I'm looking at is a lake, a body of water, a thing heavier than air and craft, and atmospheric phenomena. And when you look at the feature vector, this is we use these algorithms to extract features by, instead of going by the very end when they're telling you what are the class or what type of elements have been identified on the image, we rather looked at the latent space, or the most synthetic representation of the image that has been input in the model, and that's our feature vector. There are other ways that we could also try to play or extract features from images. In this case, we're going to use a method that is called Fourier transform. So what I did here, I looked at the image data and I flattened it, which says that my image has 180,000 dimensions. And I'm going to apply a Fourier transform to this data. And what you're going to see is that now my data, let me show you the thing. It is a long list for one image of 180,000 dimensions. But because we Fourier, we could do a synthesize our data, and we decided to only look at this part of the data, which is from the first until the 15, and you see that now our data is much shorter. In text, you could do similar things. So for example, in this case, we could look at based on a trained model to do sentiment analysis, which is by defining whether this text is positive, neutral, or negative. You could use these as a three-dimensional feature vector to describe the text that you have, which in our case, we're just getting some quotes from these be or not to be text. Or you could do, in this case as well, using a natural language processing, which is, let's say, the grandfather, the great-great-grandfather of the GPT right now. So what we're doing here, we are creating tokens to describe the words, and these are living in a feature space. So every word is related to any other word. So what you're having here is a synthetic feature vector describing the text that we saw on top. All right, very fast, right? So I'm just here emphasizing that we could see that the ways of seeing our data will influence how your machine learning algorithms learn from the data. Because in a machine learning process, you do have 3 steps. So there is the teaching, which is about curating your data set. There is the learning, which is about the algorithm architecture, and then the way that it's going to learn what we've set on the data set. And then there is the inference. So what we want to emphasize today is the curation of the data set, and the way that we decide to encode the feature vectors really influence the final output that the algorithm will give you. So what we're going to do here, this section over here, it's allowing you to load a specific data set. And as I said, if you go back to the PDF, I have set up several data sets for you to play with. As I said, I'm fascinated with spirits, so I'm just going to select the one with Georgiana Harrington. And then we can play with that. So the idea for this workshop is to understand that these the digital allow us to have a continuous movement. It's not discrete, but a continuous, because an image can become numbers, can become text, can become sound, can become video, can become 3D. So that's really interesting to think about. So right now I've curated these data sets for you to play with, but as I said, you could really look at any other data set that may be interesting for you to work with. So how this works, the first line that you have to run is identifying where you save your data. So here I have my data saved on this particular folder. And as I said, I'm going to be working with this data set. So now I have defined on my directory where my data is. And then this one, what it's doing, it is importing all the images. And then in this line over here, it's going to resize the images and define a predefined size, which is saying that every image that I have collected, though it has different size, everything is going to be at 300 by 300 pixels. And then since I want the images to be cropped by the center, I'm going to take a collection, 250 by 150 pixels. All right. So once we've done that, I set up 4 ways for you to work with your data set. So you could decide to encode your data by using the edge analysis that we just saw here, right? So we want to focus on the texture of these images, or we could decide to encode our database on the colors by using RGB analysis, or you could decide to do it through Fourier analysis or through feature extraction method, which is here saying what elements the algorithm has identified on the images. Because I am interested in perception, and for me, color right now is something that I want to look at, so I'm going to encode my data through RGB analysis. And the way, I forgot to mention, the way to run this notebook is by doing Shift-Enter while you're on the cell. So I'm not going to run this as I'm streaming, because I'm sure my computer will hate me. So I've already run this RGB value. As I said, just sequentially run this line and this line. And then what you will get at the end is a file that is going to be saved in the folder where you have your data. So as I told you, I'm working with this spirits data set, I call it like that. And then at the very end of the folder, there is this new file that was created, which is saying this is the feature vector. We're using RGB feature extraction, and it will have the extension of that M. So now what we're going to do, we're going to use the same neural network that Julian introduced just before. And if you want to know how it works, I've also prepared a little bit of explanation about this. So right, you start with a random grid that has the same dimension. In this case, are the colors. How to find the best matching unit. So you need to say, or the first, I'm going to look at my data once, and I'm going to show it through the randomly initialized grid. And then I'm going to try to find where this one data point fits within this randomly initialized cell. So it says it's over here. So I'm going to, in this way, you could say the moment that my data point finds its best matching unit, it not only gets placed here, but it also influences everything around. And that's the important thing with self-organizing maps, is that you're not only modifying the grid based on the new data point that is being shown to the randomly initialized cells, but you're also influencing everything around. So imagine doing this for about thousands of times, which is what is happening when you're training a sum. It starts like this if you're playing with colors, but then if we plot the data looks more or less like this. And when you're training the sum, what it's trying to do, the first iteration is trying to map each cell with the corresponding color that you're looking at. So now, because it's not trained, it feels at random. But once we're starting to train the sum, I hope my computer doesn't crush me. So we can see that the grid started to adjust to the data. So you're seeing a much more, we call this a spectrum of similarities, or a landscape of similarities. And so we could see, this is more or less what's happening with the training. Just be patient, because here is going to show you the epoch. So right, starts at random, and then starts looking at the different testing out when each epoch is happening, how the grid is being extended, moved, and shaped depending on your data. So this is really interesting, because this is an unsupervised clustering algorithm, which means that we're not predefining anything that has to be learned, but this algorithm allows us to see a rise of patterns on the data. So this could be used as a navigation tool for understanding the design space where you're going to be working on. So in our case, let's say in my case, I will be working on this data set of spirit, or images that are about abstract art, let's say like that. So now that we know how the self-organizing maps work, I want you to go here. We're going to build up these self-organizing maps. And similar to the feature vectors, if you close your notebook and only run it until the feature vectors, you don't have to, you have to run this line again. But if you're following along with me, you don't have to do it. But just for the sake of moving, replicating what you could do. So here we define where our data set is. So we go back to data sets, this one here. Then when you open this line here, it's saying, show me where the feature vectors are. So you need to go back to your data sets and to the folder. And then you have to scroll at the very bottom of your folder. There is going to be, or at the very top of your folder in this case, it's going to be the feature vectors that has been extracted. Then we're going to create the vector list. And then now here you could define what's the size of your sum. So in this case, I am training a 15 by 15. You could do a 10 by 10 depending on what you want. So here is just confirming that you have 180 dimensions. And there's a 15 by 15 sum. Here, if you want to increase the epoch for training, you can change this number. In this case, I'm going to train through 8 epochs, and you see epoch 1 till 8 has run, and then here is just saving the data. All right, let's try this. So we can visualize the output of the self-organizing map. So the first line that you can run is seeing how many elements you have in each cell. So it's saying cell number 1 has 44 images that are alike, cell 225 has 26. I'm also giving a way to map those feature vectors into two-dimensional colors. So you have many ways to render these. I've decided to do the lake colors, which are these ones. I want to see, this is helpful to see how well your self-organizing map is trained. So it looks like it's well trained. You see there is a smooth spectrum between different colors. This one, it will take a little bit of time just because now it's trying to find the an image within this cluster to be mapped on top of instead of the colors or instead of the numbers per image. So this is going to take a little bit of time, but here we are. Let me wait a second. I want to zoom out so you could see it. Oh, wonderful. Let's do this. Okay, maybe I'll just do this. So now we have our self-organizing maps. If you remember the PDF that we just saw, there is a randomness that is really hard to understand what the data set looks like. But with these just quick feature extraction approach and self-organizing, this data set has been organized in a way that I can understand some patterns that are relevant for me to start working on what I want to do in this tutorial. So with this section here, what we're going to do, and this is helpful just for exploration, I will put the 3 renderings of the sum in one line. So it can help me know, all right, this cluster over here, it has 44 elements. I want to see what they are like. So here I've given you an option to navigate cells. So here, if you change these to cell number 1, and I want to see the up to 20 images, I see that these are the images that are in this cluster. And there is quite a consistency in the cluster. I've given, because we're trying to do this experiential perceptual approach to space, I want to test out 3 ways of rendering this cell. So for example, the first one is treating every input of this 20 list as a channel to render an image. This one is highlighting the color that is more prominent on the list. And this one is by highlighting the texture that is more prominent. So now we're looking at one cell in its one rendering. But for example, I think this is an exercise that I do with my students just to kind of grasp what this one cell means. We can do the same thing, for example, with cell number 5, which is telling that there is 10 images here. So I'm going to look at cell number 5. It's giving me this output. And then now we see what we're looking at. We can also play with something much more, let's say, guided. So here, if you, from this list that you're looking at, there are just very few images that you would like to keep working on. So for example, this could be one. You just replace it here by doing copy paste. So you can copy this one, replace it over here. You can do up to as many ones you want. So for example, here, I'm going to do this one. And then you're going to have the same process, which we did with all the images included on our cell exploration, but we're going to do it by selected images. So this is a fun exercise to create or to start thinking about how to generate an image, which is not an interpolation between your data set, but is your data set itself. So this is an approach to image generation, but being indexically generated. All right. Why this is how we got into here. If I'm going fast, you let me know, Neil, okay? Because I always get excited and I just go fast. But
great, recording it so they can listen to it again. Don't worry. So
okay.
Yeah.
So we're going to do an interactive selection because I wanted to show you several ways that I've used the self-organizing map, right? The first way that I use a self-organizing map is just to navigate my data set and to be able to grasp a concept or an idea that I could see, that I'm projecting my creativity on top of this. Because my thinking on how AI is helpful for architects is AI, it's becoming this instrument or tool that knows, or because it has seen so many things and it can help us discover. But I see us designers and humans as able to create and to project creativity on what we're looking at, what has been shown to us, and to imagine. So I do this exercise to trigger imagination and to find creative ways to describe space and to describe the way that we speak about space. So now we're creating these concepts around specific cells that you're projecting your creativity. You can call them however you want. What we're going to do here, I want to talk about, if you follow along the description of what we're doing, we're just here, right? So we're creating these atmospheric images. What we're going to do now, we're going to create a training data, right? How can we use this unsupervised method for a supervised learning? And we're going to use this to train a classifier. And what this classifier is going to do in this exercise, you could use it any way, and I've used it in different ways. I can, if eventually I can show you different published research of the way that I've used this code. So in this case, I want us to focus on capturing abstract concepts like calm, for example, and I want to find a word that could be contrast with it, like, for example, excite. So I want to create or train a classifier that is able to define or to find the difference between what I think calm is and what I think excite is through a data-driven approach. So what we're going to do here, when we run this line of code, we're going to load this grid or this train sum, but we're going to be able to manipulate it in a way that we can select. So for example, my class number 1 is going to be about what I consider, how am I reading this data as to give me examples of calm. So I'm gonna start like selecting some of these examples that I think are part of this concept. As I said, because I want you to like take more time to do this, I may be just rushing to finish and to show you the result. So for example, I selected these mini cells. So I selected cell number 77, and if we go back, 77 has 77 is here, has 8 images, and then we can also see cell 199, 110, and so on. If you run this line over here, it's gonna collect everything that I've selected that are within this idea of calm. If you don't want cells, for example, I think I did a mistake, you can unclick everything and you can start from the beginning and you can say, oh, I think it's this one, I think it's this one, this one, this one, this one. And so you could really start doing, you can always redo and there is always a way to go back to your initial clustering. So here we go. And then say, oh, maybe this is something that I want to try again. So you can always do this how many times you want, just so you're sure that what you're selecting is what you really want to see. All right, so now it's going to be my final test. So I'm going to like set up my calm data set, which looks like this. So you can say up to 20, for example, and it's going to give you other examples. All right, I'm just going to make sure that we're getting examples that are good. All right. Here we have it. And then class number 2, we also have to run this cell. It's going to give us a similar grid. And then in this grid, we can now select what we think is excitement, or how can we describe, or how can we project this idea of excite on a data set. I'm going to select a few of these just so we get it. As I said, you will do this with more time and less rush, so I can show you the output. So for me, these are images that I consider to be exact, and I can show more. Right, so how do we make use of these two data sets that we just created? So I created here a very simple classifier, which is taking class number 1 as to be calm and class number 2 as to be excite. If you want to create more classes than the ones that I just set up, you could copy paste this section over here and then create class number 3 and replace this name, and then just add here the other classes that you want to have. So here I'm going to run this line of code, and you're going to see that my training data, it looks like this. What I've done is that I've taken the first third part of the whole data set as to be my test data, and then the other 3 parts to be my training data. And it looks like this. So now when I run my classifier is going to show the way that it's training. So you'll see that it's testing some algorithms, and now what we have is a logistic regression that has 2 classes, and it has 50 examples to train. Right now, I'm going to try to see the metrics of my algorithm, and then it's saying, oh, you say it's not very, I mean, it learned, right? It could be close to the, let's see. So we could ask for, one helpful thing with mathematics is that you could really check other things that you can ask. So for me, I like to see what's the accuracy. So if I copy this line of code, I can see make test data. So I want to see how accurate this classifier is. And it's going to tell me that it's a 76% accurate. So I think it's not the best, but at least it can give me a good enough example. So what you could do is like you could go back to your training data, to your folder where you have your data, or you could bring any of the images that you have created here and then try to set up whether they are within these 2 classes that you've created. So according to my classifier or my the algorithm that is able to encode my perception, this image that I have here should belong to the class excite. So in this way, what we could do and what I do later is to try to think about how do you experience a site in terms of words, and then map these concepts along a space. So this helps you create a perceptual map that can later be rendered into space. All right, I think that's it. As I said, if you want to get into what I just showed you, you could come to the AI Share Lab website on teaching. At the very end, there is this tutorial that I just created and show you. It has a little bit of literature. This is a very simple and easy to follow article about what we're going to do. Then I also have the 2 documents, this one that is the data set and this one that is the code. On the data sets, you could quickly download any of these data sets that you want to work with. And it also has a step-by-step description of what we just saw today. And I encourage anyone who has been using this tutorial to get to the last step, which is using all of this perception, image generation into a spatial walk, let's say, to space. All right. That's it.
Thank you, Karla. I was actually waiting for that final thing. What does it all lead to? Great. So you give us the link and we can go and explore it again in more detail. But that was packed full of information, that presentation, and super clear. So thank you so much. Thank you. With our final session is with Serjoscha, who is here with us now. So just not necessarily I've introduced you already, but please just go ahead and share your screen. You've got some tough acts to follow after all that. So great. Welcome.
Thanks. Yeah, thanks for having me. I will just jump right in. My topic is, the screen, okay. Multimodal large language models in action practical use cases for data-driven design. A bit of a disclaimer for this presentation. It's more meant as a teaser and starting point, but I think that's clear. To dive deeper, I also have prepared a GitHub repository where you can see all the code snippets and examples and some more detailed introduction to that. So can all be tried out in detail later at home, so to say. Now a bit of background to my perspective and to frame kind of the rest of this presentation and demonstration. When I say data-driven design, I actually rather mean data-driven urban design. I come more from this urban scale perspective. So data and performance-driven urban design is kind of my field of interest. And there was quite some development, I think, the last year. So we can kind of compute hundreds of design variants of urban quarters like here. We can assess them with dozens of simulation models. This can be traffic, that can be space syntax related, for instance, but also microclimate and a lot of other things. So we can generate a lot of data points. We can take the perspective of different domains, experts and expertises, as just mentioned, and assess one single, even hundreds of design variants with all of these different perspectives and from across different layers. On the one hand, that's great to make more informed decisions. On the other hand, it's super complicated then with that much data to actually make sense out of it and to make decisions and kind of navigate through this complexity of 100,000 of data points. Like this example, this CFD simulation, wind comfort simulation here alone, you could say has a few 100,000 data points, right? It's not just one number, but the whole map. And imagine having dozens of that to kind of navigate through at the same time. And that in urban planning, I think is super important, right? Because traffic and microclimate and social aspects, they all kind of affect each other and are moderated through the spatial layout and design. So from there, we would say even that we can do all the simulation assessments and variations, we kind of have a knowledge action gap. We have the information, but acting on them is quite tricky. Also, let's say I have now 5 simulation models on this model, but maybe I'm not really a CFD expert, right? I'm a generalist. And I know perhaps I can see there are some red aspects, some red dots on the map, which mean high wind speeds, which is probably not so good. I should kind of solve that problem. But how to solve that, that's another thing. The model, the simulation doesn't tell me how to actually improve the situation, right? That's why this term here, knowledge action gap. And that's kind of how I want to now transition to the topic of large language models and how they can kind of help in exactly alleviating the problem I just described here. I think there are tons of potential use cases for that. Super exciting, especially with vision-based models, and also can take images into account. And here are some examples of what I could imagine are kind of definite use cases. So you could use large language models as domain experts. You could train, fine-tune them, or just use a general capability to say, to ask them, take a look on my project from a traffic planning perspective, or from a community-related perspective, or microclimate perspective. You can also have actual simulations running and then use these kind of models to help you interpreting the simulation results and suggest actions. In that part, I'm especially interested about to kind of close this knowledge action gap. And then another great use case is to use it for to control parametric models via speech, images, reference images, or text. And if you have seen or used such parametric models, they can easily have thousands or 50, 60 parameters or even more. And if you're not an expert for that or haven't used it a lot, then it's quite overwhelming. I think this is another great use case for large language models to kind of take away the complexity and let you to work with images and speech, and then just generate the parameters for the model based on these inputs. And imagine to kind of chain these things up together in an agentic workflow, right? You could say we have a design option. Our expert domain expert models assess it from different points of view. On top, we also have a simulation running, and the model is kind of analyzing, interpreting the results, and suggests actions that can be translated in a new set of parameters. Yeah, so in theory, this could be built up to quite complex agent systems utilizing large language models. To make that work in practice, I think that's would be quite complicated, but definitely it's on the horizon, I think, how to get there. Now, that's kind of the background. The tools I want to show today, now it gets a bit more concrete, are first of all Rhino and Grasshopper, then ChatGPT, and also a platform called N8N, which is quite interesting. It's also a low-code platform, operates on the web, where you can create workflows connecting different APIs together, using also calling into various large language model providers. And this is quite cool because you can build these kind of flows and use them as a backend, because you can call all your workflows via an API from Rhino Grasshopper or from a Colab or anywhere else. So this is actually super cool, and I think can really increase prototyping speed. Yeah, so these are some ways to implement these large language models into workflows. You could also use, of course, Python scripts, deploy them somewhere, and so on and so forth. But these are kind of a bit more simple ways to get started and start getting your head wrapped around these topics. I want to dive a bit deeper into N8N. It's an automation platform like Zapier or Make.com. You could do workflows like, let's say you get a new email to Gmail, you use a GPT instance to analyze the content of the email, and it should classify it as important or unimportant. If it's important, you use the Telegram chat node to send you a message to your phone on your Telegram app. That would be very simple. So all of these kind of nice to have workflows can be done quite easily, but it can also be used for bigger workflows and setups. And as I mentioned already, all of these workflows, you can trigger them via API calls, right? And I think this makes it super interesting tool to increase productivity and prototype in a very fast way. So in this sense, I will also show and provide a snippet to do exactly that, where we have a workflow using a LangChain node here, large language model, and that can be triggered. That's hosted online on N8N, but can be triggered through Grasshopper with this kind of really small setup. So the heavy lifting is done not on your Grasshopper canvas or other script, but somewhere else. Much nicer. Now on the Grasshopper side, I also have some snippets that go into the examples I just showed above. For instance, just like fetching some images from viewport or screen grab, but also essentially Python scripts that call into the endpoints provided by OpenAI, and also one for kind of to utilize the images there. What you need for that is your own OpenAI API key. Yeah, I have prepared these examples here. One is to just describe an image, for instance, what's happening on your screen, which describe a Grasshopper script, for instance. Then the more interesting system of experts, there the idea was to say you provide the models, we call two models. Each model gets the same set of basic instructions and context information, for instance, the image of your urban quarter with some stats to it, and then they are instructed to analyze the situation from two different perspectives. For instance, from the perspective of traffic planning and from the perspective of microclimate, to take these examples again. And then in the end, there's a third model call to kind of moderate between these differing aspects and views. So this could be used to kind of create awareness and get other kind of experts' opinions, potential opinions on a case early on, to kind of have them in mind, right? Then I have examples on text to parametric models. So quite easy, you give the text input and then we generate parameters for a parametric model. Then the same with image inputs. That's a bit more complex in advance. The model has context of how your quarter actually looks like, and can also make kind of spatial references. You could say the buildings near to the lake, please make them a bit lower so the views are not blocked, right? This could be possible to kind of account there. then GPT is called and parse the answer into the parameters. And then there's also workflow where I attached AI rendering API from the end, some stable diffusion model. So just to illustrate, you can build all of these workflows. They're in Grasshopper implemented, but you can also do them in NAN, which would clean your canvas and keep things a bit more clean. It would be very reusable. So I'm going to show that in the end, how these kind of workflows look like. Now, how does it actually work?
Just
yes.
can I make one comment? Could you just enlarge the screen? Sorry, put it on full screen because it's maybe. Yeah, thanks. Great.
Do that. I wanted to switch between different tabs, but I can.
Okay.
Yeah. So, yeah, how does it actually happen? What does not? I think often people think about these large language models as one giant black box. For instance, you tell it to generate me an image, and then it can do that as well. That's not actually what's happening. In fact, it's more like you have small black boxes, the large language models, and they're embedded in a whole workflow of traditional code logic, Python scripts or other languages, of course, where they work together, right? And this is one example. So you could have the user sends an input. The large language model is instructed, knows it has access to 3 different tools. One could be to generate an image. The other could be to access the internet and search on websites. And what the first language model would do, it's instructed without the user knowing to decide whether to use one of these tools or not. It will answer in a JSON format, like in a text format. And then we have a parsing component, the normal code that picks up certain keywords and could then decide, the model said we should use the image generation model. That's why we use that tool. The tool is used, return some results, and then often a second large language model call is assembling all the new information and creates an actual answer that's then given to the user. That's important to keep in mind. For complex applications, it's not just a model call, but you have a whole workflow infrastructure in the background. Another super important feature you need to know about is that you can instruct these models to generate structured outputs. Here's an example. We could have this prompt here below the announcement of an event. Please summarize the event and highlight important information. Here's the text. And then we get kind of this a bit nicer version of the initial text here on the left, where we can more easily look at the relevant information. But that's not enough to use in a workflow setup, right? Because it's still just relatively unstructured text. However, if we instruct change the prompt to and mention that it should answer in a JSON format with specific keys we tell it to use, the whole thing changes. This could be then the output of the model. And now we have predefined keys like event name, event date, locations, and so on. And these keys we can use, pick up with a Python script and do other stuff with it. So the next step would be to take this output and have a function, for instance, in Python, that creates a calendar entry on my Gmail, Google Calendar, or something else, and kind of directly translates that into something, I can use, right, into a workflow. And that's something we use in the examples provided here as well. And from the concept, this is kind of the few basic concepts when you build applications with large language models. Now, the example I already mentioned, I think, or what I find most interesting is to use large language models as kind of assistance to help you interpreting analysis results and kind of narrowing the knowledge action gap. So in this example, the idea is to say we have a wind comfort simulation for pedestrians here. And we get back this heat map. We have our buildings here, and I want the large language model to kind of help us interpret the result and tell us for particular areas what we could do to improve the situation. So it needs to find out which areas are problematic, and then also give some ideas on how to improve the situation. And there's a particular prompt structure. So first we might have a general introduction. You are a wind comfort expert. Then we have a larger section on actually providing information on the domain of wind comfort in an urban setup, right? How does forms, buildings affect wind flows. And then there's a dynamic part where we have an image of the actual situation. In this case, two images from two different perspectives. And then we can also add some text that says maybe the average wind speeds or the simulation parameters and so on. And what's important here is a good trick and strategy is to annotate the images, not just take the plain images of your 3D model, but for instance, add some building IDs on top of them, because then it's much easier for the large language model to reference particular specific areas in your image, in this case, buildings, right? You could also work and experiment with grids or other aspects, but that's kind of crucial to make them more stable and work. And in the end, then we instruct how the output should look like, JSON format in this case, send it to the model, and then get this kind of JSON structure back that we can then use in the user interface to create this kind of annotations. A bit more detailed, this is how this experiment actually looks like. Here is the prompt, yeah, the model, and then an output. Let's quickly go through it. So you see it's rather lengthy. You have a system briefing, your CFD simulation, wind comfort expert, and so on. Then we have domain expert, domain knowledge, different effects, building corners, Venturi effect are described here, and also some mitigation strategies. So this part of the prompt could be quite important to increase and the performance of the model, and also kind of restricted to answering in this domain. And you see, it's quite easy to set up because this would even work without retraining or fine-tuning the model, right? So this would be usually, I think, the first step to work with prompts. And if that's not good enough, then you would continue to fine-tune these kind of models. In the end, we have the output structure, the desired output structure defined. And then here, the only dynamic part of the prompt are these two input images and some information in the simulation parameters. Right, and these blue parts, the user will never really see. They are like hidden. And then we get outputs like here, JSON for two different buildings where the model thought, here's a problem, here we should annotate something. And then this is how the early prototype could look like in Rhino Grasshopper. You have kind of these text annotations on top of the images. That gives you some ideas what you could do there, right? So I think quite interesting direction to continue working. All right, that was it with the overview. Let's jump to a more practical approach. I would just like to guide you through this Grasshopper file I have prepared, and then dive 5 minutes into an 8N. So this is a Rhino Grasshopper file. We have here a few of these simple parametric models, and on top here, right-hand side, we have some snippets to fetch images, take a screen grab from the viewport, some basics, but also how to call into ChatGPT APIs. So here it's just Python code to essentially access the API, quite straightforward, and then some ways to input your prompts and choose which model you want to use. And here the same for an image-based model, so you can have the different multiple images at input, and then you can have assembly a prompt, choose your model, and so forth. And you would get your output. Yeah. These are essentially the parts, the example snippets I already mentioned, explaining what's on the screen, system of experts. So we could have, I put here one as Jane Jacobs and the other as Laneman, who should assess this urban design. So both of them, these are two separate model calls, make their assessment, what's good, what's bad, from these personas, so to say. And then we have a third model that says, should summarize kind of these potentially conflicting viewpoints, and then comes in, yeah, with some ideas. Then the parametric model here, you see how it works. And then we have one that's driven by GPT 3.5. It's a relatively simple setup. I can say, make the water super high, the most GFA possible, and then it will generate the predefined parameters, and we see the update. So text to parametric model. In this case, quite simple. If we look at this, is kind of where the prompt is assembled, and this is how the output looks like. And you see it just was instructed to generate these 4 parameters. So really simple. Next example is a bit more complicated, where we use GPT for vision, where we can generate the quarter and roofs. That's why we need this annotations on top of the buildings, because the model needs to know for which building it should generate which kind of roof parameters, right? So we have one set of parameters for the overall structure and one for the individual roofs. And here, therefore, it's kind of crucial to know which ID belongs to which roofs. So you could say, make the roofs near the park to penthouses or flat or in any shape, and maybe outside on the outer areas a bit different. Yeah, and the third version here, where I also changed up image model. It's a pretty bad one. Yeah, some old stable diffusion model, I think. So that could definitely be replaced. But here I use a replicate.com API, so you can essentially also use all kinds of models that are available on Replicate. A pretty cool website as well to do that. So it's just more to show these kind of workflows that are possible. So it's like also what you can use here is reference image to model parameter generations. You could show an image of maybe Soviet blocks style, and then it will generate this block structure or something else, and it will look more like an old town in Central Europe. Okay, now we rush to that. I just want to show you two more things. We still have time. First of all, this wind simulation example that I already mentioned. So we see the simulation result for wind comfort. We see buildings, again, they're annotated with IDs on top of them. And let's dive into the script here. We have the instruction, the analysis and domain design parameters. This is essentially what we have looked at here in detail already. And then the input images, and we can now activate it and see what it comes up with. That will take a little bit, because in the domain knowledge part of the prompt, I also added some images. So this is definitely something one needs to think about in terms of performance and also cost of the API, how much and how you want to embed information. You could also think about retrieval augmented generation, of course, for more complex topics and those kind of things. So this will take like 20 seconds, I think, with GPT-4o to process, and then we are getting our annotations here for different areas, and yeah, kind of potentially helping us to kind of make actions, derive actions based on these kind of analysis results. All right, now the last part. So you see it's quite chunky here, all these set up with the prompts, text fields, and so on. Not really very pretty, also not really well to maintain, to be not very maintainable, I think. So shifting that to some sort of web-based service makes a lot of sense. And with N8N, you can also connect it with a lot of more things. So just let's have a quick look how that looks like. So let's go through this code snippet here. The first thing we have is a webhook node. This is kind of creates an endpoint in the internet, an API that we can call from this grasshopper component here. You see, we just put the URL of that endpoint here. And this makes this definition, this workflow here, accessible from other places in the internet. So it's a little backend service, you can see. You can have a look inside here. It's quite simple. You just add this node on the canvas, and then you can give your endpoint a name, even here. I call it param modal, and then you get the URL. Top here, you can just copy paste it. The next is I create an AI agent node that you can see here. There are a few settings. System message, very simple. I just your Apple Assistant, but you could put whatever you want in there. You can then choose a machine learning model. I use OpenAI, but it supports all others as well. So I can also delete that, and then you see kind of the options of different providers. Yeah. quite straightforward. You can also add a memory that makes it that enables you that you can chat with the model, so it's not kind of keeps track of messages you have sent before. And you can also add tools here, so actually quite advanced methods. So, for instance, the Wikipedia tool that's predefined to search wiki articles. But you can also code your own ones. It's always the coding possibility. You can also call other workflows. That's also quite cool. So you can build quite powerful agent systems here in a very short time. So after it run through everything, we need to send back data to the Grasshopper script in this case. And this happens in this kind of respond to webhook node. We can test it. It's actually active, I think. So I can tell me something about LLMs, and place it into Grasshopper, and then this model ran quite fast. You see here's a log, and we get the result here, 1.8 seconds in this case. And probably can see if it actually looked for from the test mode. Okay. Yeah, so this is actually essentially how you can chain up these kind of workflows to Grasshopper, and then for any other services, and then make use of all the 400 other kind of the tools and integrations. And of course, there are also many more large language model agent features like document parsing, embedding, and retrieval. You can all kind of use this to do very fast prototyping. And to close the loop quickly, with a goal to close the knowledge action gap in data-driven and performance-driven planning or design. That was it from my side, and
great.
Yeah, as I said, there's a
thank you, Serjoscha. That was intriguing to see how you were connecting Grasshopper with large language models. That was, I don't know, it's kind of it's getting impossible to keep up with all these inventions, all this kind of inventive use of these tools, and I guess that's why DigitalFUTURES is so useful. To be able to share this knowledge, because it's unbelievable the way it's exploding in some ways. And I think the students at IAC are very lucky to have you there as well. So we've got had some extraordinary presentations today that are kind of blowing my mind. I think I need to go take some time off and go walk on the beach or something after this. This is an extraordinary session. And the good thing is, of course, they're recorded, so we can go back and look at them in detail. I'm just wondering if there are any questions in the chat at all that have been asked. I don't know if Samara, you can have a quick look and see if anyone's on the chat. And it would also be kind of interesting, because we got you together as a kind of group, whether you'd like to sort of kind of ask each other questions. It's certainly an extraordinary session today, and I think it lived up to its billing as being advanced for sure. That's for sure. Do we have any questions in the chat, or do you have any questions for each one?
No, I don't see anything as of now on the chat on like YouTube.
Okay. Yeah, I don't know. Let me just ask whether anyone has any questions for each other. Otherwise, we can wrap it up, because I think there's so much to digest today that maybe I could ask Smara whether Smara, of course, she's live streaming us today, but is doing a PhD herself in AI and architecture. Whether Smara you have any comments from today's session or thoughts? Oh, you're muted. You're muted.
It's not really a question, it's mostly a comment, but I really feel like the discussion and the debate is going a lot more towards 3D generation rather than 2D images. Because, to be honest, we said that last week too, like architecture is a 3-dimensional pursuit, it's a 3-dimensional exploration. So it only makes sense that it goes that way. But the real question is like, what, realistically speaking, what can we do with the output? Are we kind of like transferring into an age where even our like profession is going to be dealt and managed in Omniverse or in the metaverse? Or are we really looking into how we can actually build those AI generated spaces? What do you guys think?
Maybe I'll jump in. I think just seeing all the startups that are coming out now, it's clear there's not one market winner. There will be in a few years. It's interesting to see the big players are not yet making that move or almost expecting them to. But at least in terms of 3D development, there's very tangible products that are coming out which give you really considerable efficiency gains, and that's today. I think what's been clear in today's conversation is that there's this push, maybe in 3D, also in the other examples with Julian and Karla, about having more control. I think all our conversations are about control, but also our agency and making use of data. So it's maybe less about those early days of Midjourney or image generation where we were, we were still exploring like what's the text prompt, what can it generate? Now we're entering this secondary phase, which it's, what are the practical use cases? How can we give meaning to data? How can we, have agency as designers to create, our future worlds in a critical way? There's always that discussion, but yeah, it's interesting.
Yeah, I would add, I think as of now, so far, I'm still quite optimistic. And I feel very enabled by all the developments, I think, in the technologies that is there. So I'm quite excited. I think it really can boost productivity. You can do more, I think, every individual. But yeah, who knows how it is in 5 or 10 years. If they're so good that this is also skipped and they take over jobs or something, but as of now, I think it's just incredibly enabling to have these tools also so easily usable, right? I think some technologies existed maybe a few years ago, but the usability is user experience is also exploding, I think, also for the open source community. That's quite
I think having an analogy to compare what AI is today, I think thinking of it as a new brush, if you're thinking of we've been generating content forever through technology for a long time in history that we see this. But for example, if you think about AI as a tool or as an instrument, you know that, for example, if it is a tool like a hammer or a motor or something that is built to be very precise and optimal, you know when do you have to use it. But if you think of it as an instrument, like something like a violin, a piece of paper, or even a computer, the object itself is not predefined to the output, and it only articulates a really meaningful output depending on how well the user, the designer, the architect, whoever is playing with the instrument about it. So I think thinking about whether it's 2D or 3D, the way that AI should be used, maybe too much into detail as to how can we, yes, as you said, feel enabled by this new brush, by this new technology that can help us encapsulate all of these complexities that architecture is, because it's not right, only images are only 3D. It is much more complex because architecture is as a way of synthesizing community, stakeholders, the architect, the site, the weather, like all of these different examples that you did. How can we feel enabled? And I think that's what's happening today. Yeah, that's what I wanted to say. That probably we don't have to talk about whether it's 2D or 3D. It's more about how can we feel enabled with this and make the best we can do, either using it as a tool or as an instrument.
Yeah, I can add a bit on that note. I think very much in a similar line of thought that Karla just said. And I think the relating also to what George was mentioning earlier is that the control, I think, doesn't come from models that become more advanced, because at the end, those models, especially within architecture, they will be striving for a general kind of interpretation. But I think more and more it will become important that as architects we have the kind of intent and let that come through in the generation, which will come from actually understanding what these models do and creating the biases in the data sets that we want to instill within the design that we envision. And then also in terms of the 3D generation, a project isn't just 3D. I mean, there's, I think everyone that manually made a model of a project, you end up working into one part much more than into other areas. And that is an entirely different workflow of a three-dimensional part than the overall massing and the context. So, and that's currently not really coming through in these 3D models. Now, whether that might happen or not, it's hard to say, because in the same way that the image generation is currently happening, it's always one slide. And you can then, through a latent walk, kind of get a rotation of that, but it stays in the same modularity of that particular image. To then get another image that relates to it in a project manner, I think is a very different exercise, which will still, at least at the moment, still be kind of the responsibility of the architect to envision the overall project and the overall intent, in the same way that the writing about a project is as much the architecture as the visualization. And then I think this is relating to what Karla is saying, that architecture relates also to the instruments that we're using. An historical example, which I think gets used at the chair where I'm doing the PhD and where Karla did her PhD, is Alberti's perspective drawing. I mean, before that, we didn't know as architects how to convey a perspective drawing. That wasn't part of the discipline. It was plans and sections. But that ability to start mapping 3D onto a 2D plane opened up a new mode of communication and creation for architects. And I think in a similar way now, AI and computation can be seen in that context, in that it gives us a new way of communicating, a new way of rendering our ideas onto a completely different plane, which isn't two-dimensional, it's n-dimensional, it's kind of in the entire movement of that. But we still need to gain control of that. We need to familiarize ourselves with it and then see where that takes us. But I'm not at all worried that it's going to replace the discipline or the profession at all. I think we just need to become intelligent with it and kind of learn how to work with it. Yeah.
Maybe I could just say something, because I don't know if you know this, I was the translator of Alberti, of his book on architecture years ago. No, I think you're absolutely right, Julian. I think, and I've just been playing around with Runlay these days, and it does, and it wasn't a tool that was made for architects to design with. It's a tool that was made to make videos, and yet somehow you can harness it and start developing and opening up in interesting sort of ways. And I do think that is allows us to think about architecture in a very different way. It's not, well, it is kind of perspectival, but you're kind of moving through space, and that ultimately is what architecture is about. It's about choreographing people through space. And I just want to make a comment I always make when I talk about Alberti, is that actually there's not such a big difference between Alberti and AI, because I'm sure that he would be absolutely fascinated in AI right now, just as Brunelleschi would be fascinated with 3D printing and robotic fabrication. And of course, the irony as well that his name begins in A and ends in I, but that's beside the point. But I do think there's kind of like there are many things. I mean, what's happening, it's very clear now, is this kind of explosion of these competing platforms, and I don't know how that's going to resolve itself in some way. But it's not just Autodesk now. We've got all these new things coming about, and I'm wondering how it will eventually fall out. I mean, next week we have XKool, which is, I think, an interesting new kid on the block, because it's kind of potentially challenging Autodesk, because it's much quicker to react, to respond to things. I mean, Autodesk is a big kind of company answerable to its shareholders. It can't adapt so quickly, and we've got this incredibly swiftly changing landscape. And I think the way that any company can adjust to those is going to be crucial. But I also think there are two different things that maybe we need to kind of take into account. I think over the years, what I've seen is kind of like from early days when we were teaching scripting, it was hard work, right? And then Grasshopper came along. There is, on one hand, there is this kind of shift that makes things easier. You think about a phone, how you swipe it, or, facial recognition will open it. Things are getting simpler and simpler at one level. At the same time, there is the kind of looking under the hood sort of thing, which all you guys are doing, about how do you how do you really get in there and try and make things operate in a different sort of way? And I think it'll be both in the end. There'll be these kind of super users, as Andre Deutsch's, Randy Deutsch's comment, that really in the office will be able to do all these bespoke things to operate. But on the whole, I think most people will take the easiest tool and just work with it. But it'll be interesting to see how it turns out. And I just want to say, for me, myself, writing about these things, it's kind of really challenging because there is first of all, things are shifting so quickly. You can't finish a book or publish a book and have it out to be still relevant. I mean, that takes 11 months, right? And 11 months time, the whole world has changed. And secondly, it's easy when you start off and there's a few kind of players out there, but when it gets super complicated, how do you offer an array or an overview of the whole thing? You can't. So I think we're in a very interesting kind of moment where it's a kind of exploding, and people are clearly picking up on this thing. But I think that what's going to happen in the next few months, I think we're going to get much more kind of user-friendly, I think, platforms that are going to allow a different mode of operation. But I don't know, I'm not doing what you guys are doing. I'm going to throw it out there and say, well, do you think user-friendly platforms like, the way a kind of grasshopper of the world of AI is going to be the way forward? Or maybe not.
Well, in terms of beta testing or like kind of proliferation of technology, it would only make sense because not every architect is kind of leaning into computation. So I think that's the only way forward. It's only through kind of creating a more friendly environment, API, that is going to bring it down to several different levels or even education, maybe.
It's a really fascinating debate, this question of interface. So last semester at Wentworth, I taught a whole course on physical prototyping AI tools for designers, for architects. And the whole class was no one had coding experience. So we're really leaning into a bit of physical prototyping and trying to teach people how to debug and use ChatGPT or use these tools to use APIs, to use Arduinos, and to make tangible interfaces. It was a bit hacky in a way, but it brought up this interesting discussion about, what's the role of user interfaces. There's this big trend, maybe less in architecture, towards language only, a language-based approach. You see it in Humane, you see it in so many in ChatGPT. It's a language-forward approach. Now, I really do believe that language is really having this, new emergence in architecture, and it's such a central part of a process. But it's not. I don't think it's enough. So really empowering. It's one side, you need the democratized tools for everyone to be able to access them, but it's on the other side, you really do need to teach an underlying understanding of what are the parameters, what tools should we begin integrating, and how do they work under the hood. That excludes all ethical, those are the basics. Standard of care, ethics, bias, that's a certain baseline. But from an interface perspective, for architecture, for the complexity we have, it would be too simple to have a very clean, streamlined interface. And I'll add one more point. That's why so many architecture tools nowadays, you see this recurring, they start being marketed for architects, and then gradually it becomes, wait, actually, let's put real estate in front of that. Let's put the developers or landowners or whatnot. Also architects, they're also in the picture. And so this democratization of tools really falls in hand with the future of our profession, where we really need to broaden up, what are our values and what services do we want to provide in the future.
Just to add something there. I mean, I think what is interesting is when you get these kind of large language models writing the code for you, whether that's going to be some kind of intervention that's going to totally change this landscape, or whether we'll still need guys like you to really guide us through that the whole time.
Touching upon George's last point, I feel like in terms of like where the profession is headed, every time we see a new breakthrough, like from CAD to BIM to AI, I think the field is shrinking altogether, and it's going to keep shrinking in favor of like developers or other kind of more fast-paced generative, like, professions like developers or real estate agents. So I think it's an inevitable future, to be honest, even though it sounds a little bit pessimistic, to be less and less into architecture. But maybe the democratization in terms of education will come through embedding and coding, like having some sort of like coding background to begin with as an architect. It may come from being more closely linked to computer science altogether, rather than civil engineering, let's say.
Well, I think that's exactly what's going to get much easier, that you maybe don't even have to say I have a coding background. It's more like, the 5 tools that you use to generate quite complex applications. I think that's moving really fast. Like, with no knowledge, you can probably set up a whole server in a week that runs some front end and so on. So it's quite wild, right? That this gets so much easier, and you can also just get started and experiment and get quite far. And I think on top of that, there are more and more also companies that build super more user-friendly interfaces for all sorts of powerful models, and you can chain them up, connect them, and yeah, this is really developing very fast, to a point where you might also question, do I need to know how the details work? Do I actually need to know how coding works, right? Because everything is abstracted, and then you have large language models that can do the details for you in a way, right? They have the knowledge, and if they work good enough, I think right now you should still have an idea what you're doing. But a few more generations, maybe they are so trustworthy, let's say, and robust, that it's like you use a user interface like in Rhino, right? Well, a CAD program. You don't really know how the math works behind that. But
yeah, visual program definitely helps if you have an idea of what you're doing. But you're right, like there's no hard coding really involved. It's mostly like visual
I'm not sure.
programming.
I think there's also the part to consider is what architecture as a broader definition outside of the built environment, what we're actually good at. And it's the thinking in abstraction and thinking between different modes of representation, like moving between plans, sections, drawings, atmospherics. And we're quite naturally suited to understand that and grasp that, which I think becomes more and more important in the context of when we're dealing with large data sets of multimodalities. And then being able to kind of grasp how these tie together, I think is a very strong aspect of how we're able to think and how we're able to make connections and put forward ideas, which I think that's why I would say that computation and literacy in computation is actually quite important for architects to be able to understand the granularities in that and not just stick to, let's say, a production pipeline. I think the architectural thinking is very relevant to that process, and because of that, also tied to the more internal processes of computation if we're using them in discourse. Yeah.
Well, I think the one thing that we also shouldn't overlook is that in the end, it's about having a good eye for things. I mean, that's really a skill that can never be overlooked. You certainly can't do anything in Midjourney unless you know how to select the right image to then breed it further. So I think that's going to remain out there. But we should try and wrap up. We're approaching the 2.5-hour mark. This has been incredibly intense as it is. I mean, I think this is an incredibly useful resource to be able to put it online for everybody in terms of democratizing things all over the world. And as I was saying last week, I mean, basically, the challenge is, how do you teach this stuff when there are only a handful of people around the world who really can master it? Well, the answer is you have a platform where you bring those few people together. And I just want to thank you all for your contributions today, because, what I think is most reassuring about the Digital Futures project is we've managed to persuade people to share their passion with other people, and I think this is what keeps it alive as a kind of a completely free platform, which people are generously giving their time. So I want to thank you for your generosity in sharing your ideas out there, and fabulous session, absolutely fabulous, packed full of information. I also want to thank those who are behind the scene, who are helping Smaro and the whole entire Digital Futures team, who are Sarah, who was putting the images together, and Michael, and so on, others, and Bavlina. There is a whole group there that's behind this, and thank you so much for all of this. So let me just finish by saying, and maybe I can share my screen again, that tomorrow I'm going to be talking tomorrow, which is going to be a tough thing to do. This should have been the introduction at the very beginning to our series on AGI, but Joscha Bach had to go at the very beginning, so I'm now doing it right after one of the leading figures in the world, and it's going to be, for an architect to try and follow that, it's going to be very difficult. But Stuart Russell, of course, was on last week. Anyway, so I'll be talking about a kind of an ignorant architect's view of how you approach AGI, myself being the ignorant architect. And we have then a series of other sessions on that, in which Smaro and Karla will be joining us for the following week of how do we engage with AGI for designers, and then Blaise Aguiriakos, who is an incredible figure and super clear, followed by Carl Friston, who is a kind of godfather in himself and an incredible name. So this is a series of tutorials on a Saturday that goes alongside a series of more abstract theoretical debates, shall we say, on a Sunday. But it's all combining to give us a kind of a spectrum of an understanding of this new world. And so I just want to thank you all again, and look forward to next week's session with XKool LookX, and tomorrow's session with AGI. Thank you again, everyone. I'm just going to play us out without any sound, but playing us out with the our jingle. Okay, thank you so much, everyone. Thank you.
Okay, I've stopped the streaming, so we can just leave the meeting.